So much as you might understand how the internet works, whether it's HTTP that transports data or HTML that is that data, and as much as you might understand some of the fundamentals of programming like loops and conditions and Boolean expressions, variables, and more, it turns out there are so many different ways in which you can implement those ideas. And so indeed, when it comes time to actually build a website, a web application, a mobile application, it turns out that it's rather non-obvious where to begin sometimes, if only because you have so many options ahead of you. And much like the world of clothing and the world of fashion more generally is constantly evolving, such that what is cool and appropriate to use now or to wear now might not necessarily be appropriate some months or years hence. The same can be said, for better or for worse, of the technology world insofar as humans are constantly innovating. Humans are constantly finding fault or opportunities for improvement in languages that we've used for years, in server software that we've used for years, and iteratively improving on it. And so the reality is that staying current with this whole world takes some effort, even as the fundamentals largely remain constant. And so what we'll try to do here is give you a sense of some of the languages, some of the frameworks, some of the libraries, some of the overarching design decisions that are both in vogue and both here to stay right now, as well as take the lid off of some of these technologies and give you a better understanding of how some of the fundamental types of technologies from which you can choose actually work. So let's consider for the moment the so-called front end of an application. Front end generally refers to that which is facing the user, so it's the user interface and more with which the human user typically interacts. Now, we've discussed, for instance, the world of the web and how you might assemble a web-based experience using HTML and CSS, and even more dynamically using JavaScript. But that's by using those native languages, right as they come out of the box, so to speak. But it turns out that some tasks are not as easily done in those various languages as might be convenient. It turns out that there are certain design patterns, so to speak, types of code, types of markup, types of properties that people have found themselves using again and again and again. And so much like you can factor out into your own CSS files and JavaScript files code that you want to share across multiple files or even across multiple projects, so has the world more generally realized, you know what? Maybe I should package up my CSS or my JavaScript in such a way that other people can actually use it as well. And thus have been born things called libraries, collections of code that other people have written that we can all use, often under an open source license, which means the code is freely available for the world to critique, to use, to adapt sometimes, and contribute back to. Now, within the world of the front end, there are so many different JavaScript frameworks. Indeed, depicted here are just a few of perhaps the most popular right now. But even this list is going to grow stale over the coming months, certainly over the coming years and the like. And so really, rather than dive into the weeds of some of these technologies in particular, we really aspire to give you just a sense of what's current, what should be in your vocabulary perhaps now, and perhaps some context when it comes to recruiting engineers or deciding among engineers which technologies to sort of build a business on, just how current you are, just how dated you are, and the like. But invariably, this kind of thing requires some due diligence when the time comes to design an actual project. Angular, Ember, Meteor, React, Vue, these and more are the names for various JavaScript frameworks. And a framework is not just a library per se. A framework is also typically a way of doing things. So a framework includes some code that you should integrate into your own projects, whether it's CSS, JavaScript, or something more. But it also includes typically a way of doing things, a way of naming your own files, a way of formatting your files, a way of building ultimately your application. And reasonable people, of course, will disagree. And so you'll find among several of these frameworks different design paradigms, different design beliefs, the best way as to do things. And again, different reasonable people will disagree. And so part of the process of choosing these frameworks really boils down to what resonates most with you or with the engineers with whom you're working. And indeed, what resonates above all else, perhaps, is what one is most familiar with. In fact, it's often the case that you or engineers you're working with simply have done a previous project in one of these frameworks, but not the others. And so even if that framework is for some definition of inferior, that might not necessarily be an overriding concern if you can actually build your MVP or your prototype faster with that particular framework because you know it already than if you could build it a little bit better, quote unquote, and in quotes insofar as reasonable people can disagree as to what's inferior or superior in this world, than if you were to design it using a completely new framework for which there's just a non-trivial learning curve for you. And so there's, as in the case of data structures, as in the case of algorithms, as in the case of computer science more generally, there's these trade-offs. And human time, developer time, learning time is certainly one of the resources that you have to decide how much of which you want to spend up front. Meanwhile, in the world of CSS, there are also libraries there, collections of CSS files and frameworks, really, methodologies for which you via which you lay out your site, like Bootstrap, Foundation, Semantic UI, and more. And these focus a little more so on the aesthetics of a user's experience, more so on the presentation of information and the types of user interface mechanisms, the buttons, the menus, the windows, and the like that a user might see on the screen. But here, too, there are so many different wheels that have been invented in the past. So many different people have decided, you know what, that default link on a web page could look much prettier, or that button on a web page could look much better if you used my design. And so this is what's happened. The world has created and shared with others in the world various files that you, either in the context of JavaScript or in CSS or beyond, can integrate into your own projects. So how to even begin to vet these kinds of things, particularly since in a class like this, we won't go into the weeds of evaluating these. And even then, we might not reach any sort of consensus. So the reality is typically relying on the engineers with whom you're working is first and foremost the place to start. What do people know? What are they comfortable with? What did they like? What did they dislike about some framework? Did it actually speed up the work? Did it slow down the work? Did it build up technical debt for them, so to speak? For instance, just because something is easy and quick to get started with from the get-go, is it so easy because it's riddled with poor design decisions such that as you get more and more users, maybe your application or your website's going to be slower and slower, or maybe it's going to become harder to maintain, or it's going to be harder to onboard new people altogether. There's various trade-offs there. And so considering what is optimal now, what is optimal in the medium term, what is optimal in the long term should perhaps be part of that whole conversation. Meanwhile, it's certainly a compelling thing from professional development perspective for keeping things fresh to actually go and learn something new. And so certainly punctuating one's experience in tech, should there be an opportunity to both pick up some new skills, to familiarize oneself with the latest and greatest, and not necessarily change direction with each and every fad, but generally be familiar with some of the trends in industry. And there's a bunch of ways with which to do that. I mean, one, certainly relying on Google and other search engines just to get a sense of what the most popular hits are, or search results, when you search for something like popular JavaScript framework or some such search string like that. Looking on websites like Hacker News from Y Combinator, where there's an active community of folks from the startup community, especially talking about these kinds of technical decisions and design decisions more generally. Websites like Quora or other Q&A websites. Looking at github.com, a popular website where people store their code and can actually follow or star other people's repositories of code from which you can infer a sense of popularity based on how many people are following framework X or Y or Z. But this is always a moving target. And so it's simply part of the conversation to have from the get-go. And you're not necessarily going to regret a decision if you don't necessarily pick the most trendy or the one that's poised to take over all others. And because this is a fast-changing world. And in fact, one of the most frustrating, if not expensive, aspects of this world is just how quickly it changes. And so what you design today might not be what you design tomorrow, but that's also part of the excitement of this space. So with that said, that's just a glance at what the front-end design process or decision process might be like. Let's take a look now at the back end, at least in the context of languages. So here you have even a longer list, because at least in the front-end world, recall that the de facto standard is to use JavaScript in the user-facing web browser experience. But on the back end, on the servers from which the HTML and the CSS and even the JavaScript are ultimately coming, you have so many more design decisions. So you have languages like Go and Java, JavaScript, .NET, PHP, Python, Ruby, Scala, and so many others. These are perhaps just a few of the most popular these days. And all of them have their pluses and minuses. All of them have their supporters and the detractors. And all of them have folks who already know them or who might have to learn them among engineers with whom you might work. Meanwhile, though, those languages, out of the box, so to speak, don't necessarily make designing a web-based application easy, or as easy as it could be. They don't necessarily make building a mobile application as easy as it could be. Or even if it is relatively easy, humans have found over time that, gosh, every time I build a mobile application, I'm like copying and pasting dozens or hundreds of lines of code because they all share a common framework or maybe a common menuing system or a common set of functionality. And so in this world, too, have libraries of reusable code built up and frameworks, libraries of code and methodologies via which you're building your applications arisen. Among them, Django, Flask, Laravel, .NET, Node.js, Rails, and the like, .NET being up there too, because it generally refers to a set of languages you might use as well as the framework that oversees those various languages. And there's even more options ahead of you here. So how do you begin to pick among these options as well? Well, here too, you're often guided by what your engineering team knows, perhaps what your own system administrators or your operational people know. So the folks who are actually maintaining the servers, whether they're locally on site, maybe they are the ones running things in the cloud, whether that's Amazon's or Google's or Microsoft's cloud or some other company still, depending on what that cloud infrastructure supports, might influence your decision making as to what language you might use. Sometimes the nature of your application might influence the language you might use. For instance, some of these languages make it a little bit easier to make real-time applications that support like chat servers or immediate interactivity where there's a constant connection or the illusion of a constant connection between browser and server. PHP doesn't really make that all that easy. You can do it, but it wasn't really designed with that use case in mind. By contrast, JavaScript via a framework called Node.js makes that really easy to do. And it was designed more so with that kind of use case in mind. And so here, too, you see hints of why some of these languages and in terms frameworks have arisen, because they are actual solutions to concrete problems people have experienced in the past. And some of these languages are newer than others, and so they might come with more features, so you don't have to rely as much on third-party libraries. Some of them less vetted or maybe less robust or even less secure than what comes with the language itself. And recall, too, that these languages are often constantly evolving, some more quickly than others, but there are new versions of these languages coming out. And so even within the confines of a given language like Java, might there be new and improved features every year, every couple of years. And so sometimes actually picking a version of these languages or frameworks is one of the design decisions to bear. And I would say from a non-technical perspective, most compelling is just to be aware of these kinds of technologies, these kinds of buzzwords du jour, but also aware of these kinds of trade-offs. It's not necessary to get into the weeds, I think, of understanding each and every language and what it's good for, although once you have a general understanding of this world of programming, of server-side architecture, of HTTP and web pages and the like, can you, via Google and other websites, I think start to wrap your mind around some of the trade-offs and perhaps even start to tease apart which are technically compelling arguments that you might see online versus just religious objections to this language or that, because that's often the case when folks get into heated discussions of language choices, for instance. But I think ultimately understanding the trade-offs, the onboarding time or the learning curve for various languages, the appropriateness of language for certain specific use cases like the real-time chat applications or whatever your own product happens to be. What your engineers already know, what they're good at, what they prefer to use, what language and framework is easiest for new hires, maybe 6 months hence or 2 years hence, to actually come on board and understand, so that you're not expecting the most experienced of new hires to constantly be in your pipeline. So appreciating these kinds of trade-offs and asking these kinds of questions, even among the engineers that are perhaps making the decision ultimately, is a valuable way to contribute to the conversation and take some comfort in the fact that your product need not be a complete black box. You might not necessarily be able to implement it from scratch yourself, but you can at least ask the right questions and be a sounding board for some of the answers that come back. Now, there are some fundamental differences in some of these architectural decisions, among which are around choice of database. Indeed, most any web application today has a back-end database inside of which is stored data from users, whether it's purchase orders or user registrations and passwords, and any amount of data that's collected from users at the end of the day is stored somewhere, and that somewhere is called a database. But there's different types of databases. Two of the biggest categories these days are perhaps SQL and the opposite, NoSQL, as it's playfully called. SQL being structured query language, and NoSQL referring to a class of databases that doesn't support SQL and indeed is not generally relational. And we'll soon see what that means. But even with this world, you have a veritable menu of options: MariaDB, MySQL, Oracle, Postgres, SQL Server. And then within those, within that relational world, you also have the in addition to that relational world, you have the contrast of the object-oriented or document store world, things like Bigtable, Cassandra, HBase, MongoDB, and others. And already it can be sort of overwhelming to feel like just as you're getting up to speed on like what the web is and how web pages work, oh my God, like we're just beginning to make our decisions. But generally, these decisions, too, can be guided by what your team knows, what you're comfortable with, what the price might be for some of these. And some of these are free and open source. Some of them have commercial licenses associated with them. Some of them are supported easily for you with your cloud provider, wherever you're hosting your servers, or you might have to host them yourself. So you can begin to narrow the field of options. And indeed, especially when building multiple products, might you build on past experience of yourself. So as, for instance, for the course and all of our web-based applications, we tend to use a lot of the same technologies. And only recently have we begun to transition from one main language to another, but doing it pretty much for all of our applications across the board so that we don't have to worry about some of the team members knowing X and Y and Z. It's just there's an economy to scale to focusing on relatively fewer technologies internally. But let's dive in a little deeper into SQL and NoSQL, if only because they're so cleanly bucketized into SQL and not SQL, really. What do we mean by this, and what does a database really do? So a database typically supports at least these four operations, or categories of operations, playfully called CRUD, which stands for create, read, update, and delete. Though you might see some variations on what the actual words are. But CRUD refers to those four fundamental operations. Now, in the world of SQL, or SQL, structured query language, which itself is a programming language, and it's a programming language you use to query a database, to add data to a database, remove it, edit it, and the like. Within the world of SQL, there is a direct mapping of these four operations to four keywords, four features of the SQL language, namely create, select, update, and delete. So it's almost CRUD, but it doesn't quite line up perfectly. So create, read, update, delete is the general notion of the four operations a database might support. And in the world of SQL, which we're about to dive into, might you see these four commands specifically: create, select, update, and delete. So what does it mean to be a SQL database? Or more generally, what does it mean to be a relational database? Because a relational database is often, historically, what people think of when they think of databases. And only in recent years has this NoSQL trend been catching up that changes the paradigm. And we'll look at the flip side in just a moment. So if you've ever seen this, whether it's this version of Excel or some equivalent version of Numbers or Google Spreadsheets or the like, this is kind of sort of a relational database. It is a piece of software that allows you to lay out your data in rows and columns. And among those rows and columns are there typically relationships. Consider, after all, the last time you used a spreadsheet, if ever. Odds are there was some kind of meaning if you put data in column A versus B versus C versus D. In other words, when adding data to a spreadsheet, typically, if you're using it correctly, you don't just start plopping your data in any random box that doesn't yet have a number or a word in it. You generally organize the data such that in column A might be one type of data, column B might be another type of data, and so forth. And so it's relational in the sense that the numbers and the data within relate to one another. And it's also relational in the sense that you can have multiple sheets, even within a file. So by default, with Excel and Numbers and Google Sheets, you get just one sheet or worksheet by default. But if you ever want to have multiple types of data, but all in the same file, just because it's kind of nice and orderly to keep it all together, you can click like the plus and create a new sheet and have a completely different tabular structure, a different number of rows and columns and different meanings for those columns. But somehow the data is all related. Ergo, this notion of a relational database. So a relational database stores data in tables. And a table is, in turn, a set of rows and columns. So why does this actually matter? Well, Excel is not all that powerful when it comes to large data sets. In fact, it wasn't all that long ago that Excel, I believe, only supported as many as 65,536 or 35 rows, probably. And that's because, long story short, they used a 16-bit integer, the biggest number for which is 65,535. And so Excel physically couldn't count as high as 65,536 or 7 or 8 because they just didn't use enough storage underneath the hood. But even if you had that much data, and that's quite a lot of rows, the software just tended to be super slow. At least in my own experience back in the day, trying to manipulate very large data sets in Excel, it just wasn't designed for tens of thousands of rows. By the time you're at that much data, you should really be graduating, so to speak, to an actual relational database management system, a server-driven database that actually leverages not just files, but memory more effectively. In fact, among the features you get from products like MariaDB and MySQL and Oracle and Postgres and the like is you get really smart people who have implemented the software in such a way that it makes your creates and your reads and your updates and your deletes faster than they might be if you were just storing all of your data in a big file. For instance, in a big file like Excel, if you want to search for some information, you can hit Command F or Control F or whatever, type in a keyword, and then Excel or Numbers or Sheets will search for it. But generally, these spreadsheet programs are going to search for your data pretty much via brute force. Search top to bottom, left to right, looking in every darn cell for that data. That's fine if you've got a pretty small spreadsheet. We slow humans aren't going to notice the difference. But in the context of really big data sets, tens of thousands of rows, let alone millions or billions, it does not suffice to look at every piece of data when looking for a certain phrase or a certain number or some such value. You want the database itself to do some anticipatory optimization, sort of working its magic underneath the hood using various algorithms and data structures so as to optimize those queries and to give me answers in logarithmic time, not linear time, or time that's faster than searching the whole darn thing. So at some point, spreadsheet software does not cut it, and you transition to a more proper relational database. But moreover, at that point, you have to start deciding how you want the database to store your data. Because at the end of the day, we humans generally know a little more about the programs we write about the data we're going to be storing. And by this, I mean, if I am storing a bunch of data in a database, I probably know better than the computer might know which of these values is always going to be like an integer, or which of these is always going to be a dollar amount, or which phrase is always going to look like a time of day, or a date, or day of the week, or some other such value. And so we humans can actually help databases help us be more highly performing by providing them with hints, otherwise known as data types, that tell the database what type of data to store and therefore how to store it most efficiently. Some of those popular data types in the world of SQL, then, are these. And let's just take a look at a few of these. So char and varchar. So char being shorthand for character. And it's not a single character like A or B or C. Character, char, generally refers to a column in a database that is going to store one or more characters, a little confusingly. A string, so to speak, where a string is a sequence of 0 or more characters. So when designing a database column that you know is going to contain a word or a sentence, or heck, even a paragraph, you can tell the database, hey, database, make this column this many characters wide, i.e., allocate that much data up front. But if you're not sure, as might often be the case, maybe someone has a short name, maybe someone has a long name, maybe someone has a long address or a short address. If you don't really know what the right length is for a column, for the values a user is going to provide, you can instead use varchar for variable length character strings, which is to say you specify only an upper bound. So I don't know what the longest name is in the whole world, but my name is David. 5 feels like it's kind of short. Probably some people with longer names in the world. 20, is that enough? I don't know. 50, I don't know. 100, probably. I should probably Google to find out with a bit more reassurance. But this is a decision that the web designer or the database designer is going to have to make. You can't just tell, and you don't want to just tell the database, accept any length string. Because the more flexible you expect the database to be, the more generous you expect the database to be, the less optimization it can do for you. By contrast, the more precise you can be, the more conservative you can be, the more optimization, algorithmically, the database can do so that when you ask it for data back, it can give you those answers faster. When you insert data, it can insert it faster. So the more helpful we humans can be with our databases, the more helpful the database can be in turn. And that's probably a good thing when we have lots and lots of data in users, because we want the common case to be highly performing. It might cost me a minute, 5 minutes up front to really noodle on the problem and figure out what the best design is. But that cost is going to be amortized over thousands of users, millions of users, who are then benefiting thereafter from a better database design. So where is the line to be drawn? We'll explore this in the context of an example, but it kind of depends. There is no right answer necessarily. It really depends on your use case and the data you're trying to store. With numbers, too, do you have some discretion? Integer means what it is, generally a 32-bit value, which means you can have a number from -2 billion to +2 billion, give or take. But that might be overkill. If you know you're dealing with really small integers, maybe you don't need 32 bits. Maybe you want fewer. And so you might just say, small int, doesn't need to be that many bits. I know my values aren't going to get that large. I might as well save the database space. Or by contrast, wait a minute, going to have more than 2 billion users, success permitting. I'm going to therefore want to use a big int, like 64 bits, so I can have many, 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 many users or rows in my database. And indeed, some of the most popular websites out there have run into this issue, the Facebooks, the YouTubes, and the others of the world, where they just have so much darn data, they had better not cap the number of rows in their database table at only 2 billion, because they might well have that many and more. Then why not just choose varchar with a really big number? Why not choose big int with a really big number of bits? Well, it's wasteful, right? Like, you shouldn't over-allocate, because then you're just spending more space, and space costs money and might even cost time to search if there's more bits to be looked at. And so you don't necessarily want to just cop out and say, use as much space as you want or as is necessary, because again, we can't be as helpful, therefore, to the database. Now, numbers are an interesting one. And this is true in programming languages, whether it's SQL or C or C++ or yet others. It turns out that choosing how big your data is or anticipating it kind of has some real impact in some cases of numbers. So it turns out that an integer, of course, is just a number like -1, 0, 1, and on up in both directions. But a floating point value, or float, is a real number, a number that's not necessarily an integer, but a real number that has a decimal point and some number of digits after that decimal point that may or may not be representable precisely as a fraction. So that's a real number or a float. If you want more bits or precision than that, you can actually specify double precision, which gives you more bits, and therefore you can have even more digits after the decimal point. But the key takeaway here is that at the end of the day, it's going to be finite if you're representing a number. And so if you do use something like a float, even a double precision float, which gives you more bits of precision, at the end of the day, last I recall from like grade school, there is an infinite number of numbers in the world, both integers and real numbers for that matter. So in both the case of these integer-based numbers and these floating point values, you can only count so high, or you can only specify a number so precisely. And at the end of the day, you might have some overflow where you just can't represent bigger numbers, whether positive or negative, or you just can't represent enough decimal points, enough numbers after the decimal point to represent a number perfectly accurately. And so there's this trade-off. You might want more and more space, but at some point, you can't have an infinite amount of space. Computers are physical devices. They only have a physical amount of memory. inside of them, you might have to draw a line. And so if you've ever seen some older movies like Superman 3, which has a great incarnation of this, or somewhat more recently, Office Space, where there's this money-making scam whereby the companies in question, long story short, were constantly manipulating monetary amounts in their database systems, but they were always rounding off fractions of pennies. And so the masterminds in both movies started pocketing all of those fractions of pennies, but hilariousness ensues when they don't quite realize how much those fractions of pennies add up. But that, too, is an issue of imprecision. We in the human world, generally, when going to stores and such, use only 2 decimal points of precision. But investment banks and banks more generally might actually use more numbers after the decimal point than that. And so having the ability to express numbers more precisely is compelling. Thankfully, there does exist decimal, which allows you to specify how many numbers maximally you essentially want before and after the decimal point, or the total number in question. And so that would be an alternative to these others, but it might end up then costing you more space just to get that more precision. So here, too, as with the decisions around frameworks and libraries and languages, here, too, there's a trade-off. Even at this lower level, when you really get into it, deciding how to store your data in a database. Lastly, and a little more easily, there are data types like date and time and timestamp, which do as they say. They look like dates, they look like times, they look like timestamps, like just some counter from some preordained moment in time. And these data types are commonly used, as you might guess, to store these types of data in a database. When did the user last log in? When did he or she register for the website? When did he or she buy something from our catalog or the like? You can represent those and more data types in a standard relational database that supports SQL. But you have some other options too. It turns out that in a relational database, you can be even more helpful to the database by telling it in advance if any of your columns should be considered a primary key, or a foreign key, or a unique constraint. Now, what does this mean? Well, typically with data, it is useful to be able to uniquely identify a row in your table, in your spreadsheet, without having to look at the whole row. For instance, when using Excel or Numbers or Google Sheets, you'll notice that by default, all of the rows are just numbered, 1 through whatever. That's useful because if you are collaborating with someone, or you yourself are just trying to find some value, you could just jump ahead to like row 50 to identify the 50th row of your data. You don't have to look for a specific name or address or purchase order or whatever it is that you're storing in this table. You can just jump to the row number in question. A relational database very often takes the same approach, using some piece of data, usually just an integer, 1, 2, 3, 4, just like these spreadsheet programs, to uniquely identify the rows so that you can access them very quickly via that number or that index. A foreign key, we'll see, is a notion of a piece of data that kind of exists in 2 separate tables, 2 sheets, where there's an interrelationship. But more on that kind of example in a moment. And a unique key, a unique column, is one where you should not see any duplicates. So for instance, maybe when building a website that has users register for your website, if you want to ensure that no user can have the same email address as another, you can specify to your database, hey, database, make sure that maylin@harvard.edu, or whatever the user's email address is, only appears once in a column in my database. Don't let David or not David register with that same email address. And so this is a useful way to ensure that you have correct behavior of your website and you have integrity of your data so that you don't accidentally have, say, duplicate values, which would lead potentially to ambiguity. And there's even more features you might get from a typical database. So let's indeed now try an example whereby we decide how best to store data in my database. But to simulate my database, I'm going to quite simply just use Excel here. I could use Apple Numbers or Google Sheets or the like, or any spreadsheet program. But at the end of the day, I'm really just using this because it's a program with rows and columns. In reality, if I am a business owner and I have a web-based store and I sell widgets and sprockets on my store, The reality is I want to keep track of who has bought what, so I know what my revenue is, so I know to whom I need to ship things, and so forth. And so I'm going to pretend to be the database here so that we can walk through an example where we design this database, but realize that the actual data that's being inputted by the user into my website's front end, the HTML, JavaScript, and CSS user interface, is going to get sent to the server as via an HTML form, where my backend language, whether it's Python or PHP or Java or Ruby or the like, with some framework probably, is going to be ultimately storing it in a database. And that database in turn might be MySQL or MariaDB or Oracle or Postgres or something else. We're just going to focus on what any of those databases might, how any of those databases might potentially store the information. So someone has just submitted a form on my website. They've given their credit card information and the like, and therefore it is time for my website to store this information in a database. What am I going to store? Well, if they've bought a widget, I might type in widget, quantity 1, and maybe it was Zamila Chan who bought this widget, and she is at the CS building at 33 Oxford Street, and that's in Cambridge, and that's in Massachusetts in 02138, USA. So here's some information, therefore, that I might store. This is good because I know to whom to ship it. I know how many widgets I have sold, and maybe the price should be in there as well. So she paid maybe $9.99 for this widget. All right, now let's fast forward in time, and let's assume that someone else has visited my website, and they too have decided to buy a widget, but multiple widgets. We upsold them. So a widget was bought, quantity 2. This is, say, Rob Bowden, also in 33 Oxford Street, Cambridge, Mass, 02138, USA. And this one was a total of $19.98 since he bought 2 of them. So I've just been storing this data in sort of free-form format, but each of these columns clearly has meaning. So maybe this first column should really be called product. This one should be called quantity. This one could be called name. This is maybe street. This is maybe city. This is maybe state. This is maybe zip. This is maybe country. And this is maybe total. But even here, there's some opportunities for disagreement. This is a little US-centric, the fact that we have cities and states as well as zip codes. Indeed, it might be the case that zip codes don't all follow the same format. Indeed, even in the US, sometimes people write them with 5 digits, sometimes with 9 digits and a hyphen. So there's a design opportunity there. But let's drill in deeper as to what data type these various fields should be, at least right now. Let me make room at the top here, so we can just make notes as to the data types. But in reality, these would be stored not in the table itself, but somewhere else in the database. What data type should product be? And remember that among our options are data types like these, product. Well, it's not a number, so we can knock off most of these options. It's definitely not a date, time, or timestamp. So then it boils down to, is it a char or a varchar? Oh. So char is a fixed length field, so we have to decide in advance. It's going to be 8 characters, 16 characters, 100 characters, or something else. Varchar would mean we just know the upper bound. So I don't know. Like WIDGET is 6. So minimally, it's got to be 6 characters. But then there's sprocket, SPROCKET. Not sure I've ever had to spell that word. That's 8 characters, so 6 isn't going to cut it. So maybe we do something like char 8. But there's a trade-off here. If I specify now that this field is maximally going to be 8 characters, then I can't sell anything with a longer name than sprocket. I could change the database size or the column size later on, but it's ideal to get these things right from the get-go and not to have to go back in and change your infrastructure or hire someone to come in and make modifications. So maybe that's a little short-sighted. Maybe it shouldn't be 8. Maybe it should be twice that, like 16. I don't know. And I'm not necessarily going to offer an answer here because it entirely depends on what data you're trying to store, what items you're trying to sell. This, in fact, now is even more wasteful because even though I'm now anticipating product names that are up to 16 characters, the char data type is going to use for every product name 16 characters, even if a whole bunch of those are blank because the word isn't long enough to need 16 characters. So maybe I would go for a variable length field, not char, but varchar, whereby the maximum length of my column should be 16 characters. But here, as in CS more generally, trade-off. Like, it might seem like a win, like, OK, well, if the problem is I'm using too much space all the time, let me just put an upper bound. There's got to be some price you pay. There's got to be a trade-off. And indeed, there is. It turns out that a database can generally search your data more quickly if it knows the entire column is the same width. Long story short, if it knows that this column is 8 characters, 8 characters, 8 characters, 8 characters, it can use very simple arithmetic to jump mathematically from one row in that column to another, because they're all the same distance apart, essentially. But if you have a varchar column and variable length, you can think of the column not as being perfectly smooth on both sides, but kind of jagged on one side. Some rows are short, some rows are long, and so you can't just blindly use simple arithmetic and jump 8 characters at a time if the length were 8, or 16 characters at a time if the length were 16. So it's a trade-off. If we want to be able to search through our product names quickly, might not want to use a varchar. So here too, no right answer. It's a trade-off. And it might not matter for small data sets. Indeed, probably doesn't if you don't have many customers or you don't have many products. But certainly on scale, these kinds of things matter. And even when building something that's not going to have that many users, just getting it right doesn't cost that much upfront time. The most important thing, I dare say, is to actually give it some thought and not just leave it to chance or take the easiest way out. Because invariably, over time, you will build up so-called technical debt, where you make poor decision, poor decision, poor decision, and now you have a very expensive decision later on if you have to go back and change a lot of those things. What about quantity? Well, quantity, nicely enough, would seem to fall more cleanly into one of these fields. Now, is it an integer? Is it a big integer? I think we're doing pretty well. If we need more than 2 billion products sold, maybe we're sort of a smaller shop and we can get away with an integer or even a small int. But this too would be a trade-off. How many bits do you want to spend? I would say that the default typically would be an integer unless you really are expecting a huge amount of data, billions of rows. So we might say something like integer here, name. Oh gosh, this is that can of worms again. How long is a maximum name? Maybe I do some Googling and some due diligence. That's the maximum length names. Maybe I just want to cut it off. You've probably been to a website before where you're happily entering your information and then you keep typing and nothing is happening. And that's because the programmer or the database designer has decided, your name doesn't need to be that long, or your address doesn't need to be that long. And it's infuriating sometimes because there are assumptions, naive, insensitive assumptions sometimes, but that boil down to perhaps either calculated design decisions or maybe just poor design decisions. So I don't know what is right here. 16 feels a little too conservative. So maybe I would say something like varchar 128. But even that, I'd probably want to take a look at my customer base and see if that's well beyond the limit of what I might actually need. Same thing for street, same thing for city. I don't really know what the right length is, but let's assume it's going to be varchars for those. So we'll just use a ... to suggest that it's an open question. State is an interesting one. If we expect to have only US customers, we can do a little optimization here, right? If every US state has a 2-character abbreviation, we could do char2 so that we get that performance benefit of knowing that every row is the same width, 2 characters, so long as we're comfortable not selling products to anyone else in the world beyond the United States. Zip code 2, design opportunity there. I think it's fair to say that integer, while seemingly correct, might get you into some trouble, at least here in Massachusetts, where we have a whole bunch of zip codes that start with 0. Like in the world of numbers and integers, leading zeros are meaningless. You can have as many zeros to the left of your number, and they don't change the actual value of your number. But in a zip code, it does have meaning. It is the first of 5 digits here. And so calling this an integer probably isn't very wise, because if the database is like most humans, the database might ignore that first digit. And so my zip code is going to appear to be 2138, which really isn't right. Now, we could fix that in code. We could make sure that, well, if we ever see a zip code that's only 4 or fewer digits, let's just prepend some zeros. That feels messy. If we're going to put the data in there from the get-go, let's make sure it comes back to us correctly. And so I might actually say something here, even though it looks like a number, maybe I would actually say it's a char 5 field. Or maybe it's 9 or 10 if I want to have a hyphen in there for US zip codes. Country 2, here maybe it's maybe it is going to be a 3-character abbreviation, a 2-character abbreviation. Not sure what's best there. Really depends too on what countries we want to sell to, if not just the US perhaps. So there's a design opportunity there. And then perhaps the last to consider is this total. I think it's fair to say that integer would not be correct, because we would either be rounding down or rounding up all of the money we're supposed to be collecting from our customers. So we probably want one of these. And some databases differ, but generally a data type like decimal is ideal. You don't want to even get into the business of worrying about these rounding errors or errors of imprecision, as in Superman 3 and Office Space. Much better to just say that you want a fixed number of digits to the left and a fixed number of digits to the right of the decimal place, so that you are not losing even fractions of pennies or mischarging anyone or losing out in any way. So we might use decimal in that way. Some databases, though, have an actual currency data type which operates similarly. All right. So there remains to be seen some opportunities for improvement. If I continue to sell widgets, let alone sprockets, I'm going to have more and more and more rows in this table. And if Rob and Zamila end up being repeat customers, I might have more and more Robs and more Zamilas in the same table. And as that happens, there begins to be quite a bit of redundancy. Indeed, what can you factor out over time? Well, certainly if Zamila and Rob keep ordering more and more items from my database, I could just keep updating the quantity, but that feels a little messy. It'd be nice to have a veritable history of all of my sales. I don't want to just aggregate everything. So adding more and more rows for every sale seems pretty compelling. But then I'm going to see Zamila Chan and Rob Bowden again and again and again and again and again in this table. And I'm also going to see their address again and again and again and again. And herein lies now the capabilities and the feature of a relational database. You know what I'm going to do? Rather than just treat this as my one and only table, let me go ahead and just rename this sheet or worksheet to be orders. But I could call it anything I want. And you know what? Let me create another table or sheet, and let me call this customers. So even though, again, I'm using Excel here, this is just like I might be doing in Oracle or SQL Server or in Postgres or MySQL or the like. I've just created a second table. But as per the name relational database, there's going to be a relation across these two tables now. And what's that relation going to be? Well, you know what? I'm going to go ahead and copy all of this customer data and actually cut it and paste it over into this new table called customers. And now this isn't quite sufficient. I'm going to go ahead and notice that Excel has already numbered these things for me. But I'm going to go ahead, just for clarity, and add my own column. And I'm going to call this ID. And it's going to be, say, an integer. And I'm going to call Zamila my first customer, Rob my second customer. And in this case, notice, now these unique identifiers are part of my data. It's not just part of Excel's arbitrary numbering on the left and arbitrary lettering on the top. Rather, these are now actual pieces of data in my database that will be stored and backed up and so forth. But notice, now that Zamila is customer number 1 and Rob is customer number 2, each of whom lives at these addresses, I don't have to worry now about redundantly storing that data, because in my orders table now, anytime Rob or Zamila or some other customer purchase from my website, notice I can shrink this, and I can say, you know what? This is the customer who bought this. It's going to be an integer. And you know who bought that first widget? Well, it was Zamila. And you know who bought that second widget and the third widget too, since quantity was 2? Was Rob. And if some new customer comes into my database, so for instance, suppose that someone new orders from my website, they are going to become customer number 3. That will be, for instance, Doug Lloyd. And suppose he too is at that same address, at that same zip code in the USA. But now in my orders table, suppose that Doug has bought like 10 widgets. He really went all in. Well, he too is going to have widget there, quantity 10. His customer ID is 3. And he, of course, is going to have spent $99.90 with us in total. So notice how we've kind of factored out the common information to eliminate a redundancy. Notice now that if Doug or Rob or Zamila move addresses or change their address, or if we were storing more information like their phone number and email address and other personal data too, we could change it in just one place and not in our orders table. Because indeed, there's now distinct semantics. Our orders table stores orders. Our customers table stores customers. And if we wanted yet another table, as we probably should have, it could store, say, products. In fact, there's still this redundancy. Let's go ahead and create another table called products, inside of which is an ID field, as well as a product field. And then, just as before, let's start numbering our IDs from 1. So our first product is a widget. And while we've not sold any yet, our second product, ID 2, is a sprocket. Now, in this way, in my orders table, can I store not a product per se, but a product ID? And so now, even though my table is frankly becoming more and more cryptic and a little harder for me to wrap my mind around, like what am I looking at? It's all just numbers. It is now what we would call normalized in the context of a database. And a database typically is not meant to be looked at by human eyes just like this. Rather, it's meant to be queried and data created and updated and deleted. And so there's certain commands in this language called SQL that actually facilitate programmatically, using a programming language, what I've been doing with my keyboard and fingers alone. Indeed, the commands with which you can manipulate the data in the database itself is going to be SQL's commands: create, select, update, delete, and others. Indeed, much like Scratch has the various puzzle pieces via which you can implement logic in a Scratch-based program, so does SQL have these puzzle pieces, if you will, via which you can create and select and update and delete data from your database, just like I've been simulating by using Excel here and my keyboard. And indeed, some of these more sophisticated concepts, like primary key and foreign key and unique key, now rather start to jump out at us, because if we consider what my orders table now looks like, notice that it's indeed mostly numbers, but those numbers are essentially keys into another table. In fact, if you look at products, my products table has an ID column, which has unique numbers 1, 2, and so forth. My customers table has its own ID column. And these are same numbers, but different meaning. These are customer numbers 1, 2, 3, and so forth. So in each of these tables, customers and in products, is that ID column a primary key for the customers and products table, respectively. Within each of those tables, it is that ID column that uniquely identifies rows. Zamila is and shall always be customer number 1. Rob is and shall always be customer number 2. Doug is and shall always be customer number 3. So those IDs, those primary keys, must not change. They must be invariant, and as such, they can be reliably used to uniquely identify customers, or in the context of products, uniquely identify a product. Or in the case of orders, we forgot something. It would seem valuable, if we continue this train of thought, to also have here in my orders table an order ID that should probably represent each of these orders, which is just going to similarly be an integer that just keeps track, really, of how many total orders have been placed. 1, 2, 3, 4, 5, 6, on up, all the way up to 2 billion, or best yet, even higher than that. But notice these other numbers now. The product column is no longer the name widget or sprocket. The quantity column, still just an integer. That's not anything to do with a key, even though it's also an integer. But customer is an ID. But it's not a primary key, nor is product a primary key here. In this context of my orders table, is product and is customer a foreign key, because those two columns are primary keys in two other tables. So within one table, if you have an ID, it should be generally considered your primary key, if that is the role it's playing, uniquely identifying your rows. But if that same number appears in some other table for the purpose of cross-referencing, really, is it a foreign key? And suffice it to say that in SQL, this database language, even though this looks cryptic to us humans, realize that with SQL, can you stitch these distinct tables or sheets back together? You can, quote unquote, join SQL tables in such a way that you can take your customers table and your orders table and reassemble them so that you see next to each order say on your administrative web page that allows you to see all of your recent orders, not the customer IDs of who has bought what, but actually the customer names and their addresses and maybe their phone numbers and emails and more. You can join this information back together again. And what databases are good at is doing exactly that kind of joining, not to mention searching or more. But geez, this was like a lot of work just to get to this point, right? It was pretty easy to make one worksheet, just put all of my orders in there. But then we went down this slope of, oh, well, maybe we should factor this out. Oh, wait, we can factor this out. Oh, maybe we should add some IDs here. Like, we just created a whole lot of work for ourselves. Now, I dare say it will pay off over the long run. And indeed, our database will be much better designed, where better design will lead to faster performance, less redundant storage of data, and more. But it certainly took a lot of work. So it turns out there is the opposite of a SQL database that's been in vogue for some time, called a NoSQL database, or a document store, an object-oriented database, where the defining characteristic really is that it is not SQL. It does not store data in rows and columns. It does not store data in one or more tables that can then be joined. Rather, it stores all of your data really all together in a hierarchical structure. And that's an oversimplification, because there are other features. But consider this example here. This is written in essentially a format that's called JSON, JavaScript Object Notation. But this idea of a NoSQL database has no fundamental connection to JavaScript, the language. Just so happens this tends to be the language with which these data structures are represented. The curly brace here and here just means here is an object of information. The quotes are just used around words and numbers. And the colons separate keys from values, where keys and values is a very common paradigm, where on the left is metadata and on the right is data, typically, key and value respectively. Square brackets just mean an array, which means that this is an array or a list of two values, something, comma, something, which happens to be GPS coordinates, latitude and longitude here. So what is this? What are we looking at? This appears to be an object, shall we say, that represents the city of Alston, where Harvard's business school is, where Harvard's engineering school will soon be. And so this object contains a bit of hierarchical information, not a huge amount. But notice it has an ID, which happens to be its zip code, 02134. It has a city name, Alston. Has a location, which by convention is a comma-separated list of two values, latitude and longitude. And so that's kind of some hierarchy. It's not just a simple value. And then there's a population of 23,775 at last count, though surely to rise. And then in the state of Massachusetts. So this is actually a snippet from a database called MongoDB, which is a very popular NoSQL database that stores data essentially like this. So rather than flatten all of your data, as is the case in a relational database using SQL, an object-oriented database or a document store like this NoSQL database called MongoDB really stores things as key value pairs. And those key value pairs might actually have some hierarchical structure. So if you, for instance, stored an order like we just did, instead of storing it in rows and columns, you would just store it as one big chunk of information like this. And inside of that object, an order object, might actually be the entire customer. Inside of that customer might be his or her city and state, and so forth. So there might actually be retained in it some hierarchy like you see here. And so this is just a different way of viewing the world. It has typically been a more efficient way of viewing and modeling your world, because you don't have to give, frankly, as much thought to the design and the division of some of your data and the normalization thereof. But you do sometimes pay a performance penalty. You do sometimes pay a penalty in redundancy of data, though there are ways to avoid that by reusing something like that ID field. So it really is ultimately a different philosophy right now. And it's a competing alternative to something like a relational database. And here, too, will there be an opportunity to read up on and to debate exactly what is best for your actual problem at hand. And now mobile. Up until now, we focused on the front end, on the back end of really web-based applications that you might access on a laptop or desktop or even a mobile device. But what we haven't given thought to is the design opportunities for mobile devices specifically. Indeed, most any of you who have a smartphone these days, iPhone, Android, or the like, have probably downloaded some application that did not come with your phone. And you downloaded that from the Google Play Store or the Apple App Store. And that software is quite likely written in a very specific language. Indeed, the language for Android is typically Java, in which programs are written. The languages in which iPhone and iPad applications are written is Objective-C, or more recently, Swift. And so there, too, at least in the world of iPhones and iPads, do you have design discretion over what language you use, with Swift being the more modern and the one that Apple's really been pushing. But even then, do you have the option to not implement a native application per se, one that is implemented in Java or in Objective-C or Swift, all of which are programming languages? You can actually implement a web-based application, but package it up in a way that makes it seem like it's a native application, allows you to distribute it via the App Store, via the Google Play Store, so that it ends up putting an icon on your customers' phones, but when they click it, they're not seeing an iPhone application per se or an Android application per se. They are seeing really a secretly embedded web browser whereby your application is implemented at the end of the day in JavaScript and HTML and CSS, but it's got a nice little rectangular window around it so the users don't realize that they're looking at Safari or Chrome, because all of the menus of those browsers have been stripped away. All you get is an embedded web browser. And so here, do you have an opportunity to choose among these options? And so one of the design decisions one makes when designing for a mobile user base is, do we develop an Android application? Do we develop an iPhone or iPad application? Do we do both environments still? And how do you choose among those? Well, it certainly depends on your demographic. Android is by far the most popular mobile operating system these days, but in certain contexts, a campus like this, iPhones are actually even more popular. So do you want to cater to one demographic or another, or ideally both? Both is probably your instinctive answer, but that comes with a trade-off. That certainly comes with a price. If you want to ship some new and improved tool that you want to make available to the world, or a game, or any other piece of mobile software, well, it'd be nice to have it available to all users with smartphones. But then you're going to have to know how to program in Java. You're going to have to know to program in Swift or Objective-C, or you're going to have to know how to take this hybrid approach of developing it using JavaScript and HTML and CSS. But there, too, there's a trade-off. You tend to get very good performance out of Android applications that are natively written in Java, and native applications in iOS that are written in Objective-C or Swift. They just tend to be very responsive. They tend to follow a very similar paradigm. Menus and buttons and so forth all tend to look and feel the same and therefore be familiar to users. And they're very responsive. Touch a button, something happens quickly. There doesn't seem typically to be much latency. In hybrid applications that are really written in JavaScript, HTML, and CSS, especially if they're technically server-side, hosted on your servers or in some cloud server, they might actually feel a little slower because there's a whole internet between you and your user's experience. Or they might have to download more data that would be better to just bundle up in the application itself. Or the menus and the buttons, they don't quite feel as native as the default Android and iOS user experiences. So a bit of a trade-off there. OK, so if you don't want to pay that penalty of performance and perception, implement the Android app and the iOS app. But now you need two developers, or one developer who knows both platforms. So that, too, comes with a cost, both in time or salary or talent or the like. So there, too, it's not obvious how to go. And even more recently, are there frameworks like Cordova, Ionic, Meteor, React Native, Supersonic, Xamarin, and more that actually offer yet a fourth option, whereby you implement your application in some neutral language like JavaScript, and then using these frameworks, these tools that other people have kindly or commercially developed for us to use, you can essentially convert or translate that middle language, JavaScript, to Objective-C or to Swift or to Java, or really to the underlying code that gets shipped ultimately to the app stores, so that you can actually develop native applications but in an intermediate language. But there, the learning curve might be a little higher. Indeed, the menu of options is even longer than the list of native languages itself. So that requires some learning curve or some time or talent or money again. And so there, too, there's some trade-offs. And so it really depends ultimately on what is your application, and who do you have working with you, and what is most important, and how much time do you have, and what do you view the technological horizon looking like some months ahead. So at the end of the day, these technology stacks, as they're called, are really just menus of options. And those menus are constantly evolving. And they focus on the front end, on the back end, on the server, on the client, on mobile devices, laptops, and desktops. There are solutions to any number of problems. Indeed, the process of software engineering and developing a product and developing a web app or a native application itself is first doing some due diligence and bringing yourself up to speed on what the design possibilities are, having a discussion, having a debate even with the engineers with whom you'll be working, and ultimately making the most informed decision that you can with an eye toward what is trendy now, what has been trendy, and where the industry might be going, but ultimately focusing on solving optimally your own problems and choosing among these various and ever-changing technology stacks.